Okay. Hello, everyone. Sarah. Hi, Sarah. Okay. Let's get started, but before we continue where we left off, two things. One, Claire just reminded me that 3 from today's lab did not turn in pre-lab quiz. 3 or 4? 4. Yeah, okay, 3 or 4. Yeah, please, by 5 p.m. Every missed pre-lab quiz will count as 0. You don't want to start the semester like that. So please turn them in by 5 maximum. And starting next week, morning is before the lab is when the turning in is. Okay, that was one thing. Second thing, I still have 3 pairs. Supposedly, I hope you found a project partner. So I have 3 supposedly groups, that means total of 6 students, that have not yet contacted me for a meeting time. You really need to do so as soon as possible by the 19th or the 18th of next week. Okay, so if you haven't contacted me yet, please do so. If you have no partner yet, please come up to me at the end of class if there is a problem with finding a partner. Okay, I think these are the announcements. Or reminders. So we stopped last time at accuracy. Before I go back into this, just a quick refresher, difference between precision and accuracy. What is the difference between precision and accuracy? You know this, just go ahead and quickly. Yes, Ryan? Yes. And then precision, we measure that, determine that by standard deviation and coefficient of variation, which we'll talk about that. And we stopped last time at accuracy, where we were talking about finding your true mean. Sometimes the true mean could be found on a nutrition label. If we're looking at, let's say, the fat content of baby cereal, which one of the groups will be analyzing, then you would go to the nutrition label and then compare the value you've gotten in the lab to that on the nutrition label. Oftentimes you don't have information on the nutrition label, like moisture content. You go to USDA website to get the reference amount of moisture for a particular product, say cheese. So your average you would subtract from, either you get the difference between the true and the average, you get the absolute. The relative error would be you take the difference over the true, and then you multiply by 100, you get a percentage. Rule of thumb, if you get about 5% error, relative error, this is probably needs battery. Anyway, if you get 5%, that means you have a very accurate result. 5 to 10 is acceptable. Above 10%, then you are starting to get poor accuracy. It's kind of like the rule of thumb there. Okay, bring out that piece of paper you started last time, and let's just exercise. Do some calculations, which you will be doing a lot of that next week in lab. So in lab, you will be using mechanical pipettes. And some of you already know how to use a mechanical pipette. Others will get practice doing that. And then the mechanical pipette can come with different volumes that you can either adjust or just set to the maximum. For example, 1 ml of a 1 ml mechanical pipette would be the maximum. And let's say you want to measure 1 ml volume. And then after getting the weight and the density, you got these 3 different volumes. So what is your true mean in this case? Huh? Yeah? 1 ml. So 1 ml is your true mean, because your pipette is supposedly you're gonna pipette out 1 ml. But when you took that 1 ml and you did weigh it on an analytical balance, and then converted the weight to volume using the density of the water, you get, in triplicate, you get these values. So go ahead and, yeah, so the true mean is 1, yeah. That's what you're after. You're after getting 1 ml. Anybody with values? Seems like Monica might have some values. You do?
Yeah.
Okay.
So the mean is 0.9961,
Okay.
right? And the mean is 1.
Yep.
And so the absolute error would be negative 0.0039. And then that would be the same for the relative error. And then the percent relative error would be 0.39%.
Yep. There you go. All right, so good practice. As long as you know how to get this, that's good, because for the lab you'll have the Excel. You enter the equation and the Excel will do the calculations, but in an exam, if I ask you to do it, you really need to know the equation and be able to calculate percent relative error.
So we would keep the values negative for all of them?
You can keep it positive or negative. It's just showing that the actual measurement is lower than the true mean. So it is less than the true mean. So it just gives you the direction of the difference. But you can also report it as absolute difference. All right, so precision. So the most common method for determining precision, or how close your replication is to one another, is this equation. Again, you need to know this equation, but in the lab you will use Excel to get, there is embedded formulas in Excel. Standard deviation is one of them, so you will just click on standard deviation, select your data, and it will calculate it for you. But in the exam, it won't do that. So you need to know the equation. So it is the sum of the difference of one replication, the difference between one replication and the mean squared, over n minus 1. So n, what would you say n is? Claire? Number of samples, or number of replications. Yep. So, and the square root of that. Now, the coefficient of variation is often used and preferred over standard deviation, and I'll give you an example why it would be preferred. What it does, it takes into account the mean value, or how large is your mean. It corrects for the size of the mean, in other words. So the standard deviation divided by your mean times 100, so it is a percentage. So we'll count it as wrong, or Cindy will count it as wrong when she's grading results section in the report if it's not multiplied by 100. So CV is a percentage. Please remember that. So again, rule of thumb, 5% coefficient of variation is acceptable. That means you have good precision. That means your replications were close enough to each other. Whereas coefficient of variation between 5 to 10 is acceptable. Above 10 is really close to poor precision. You have a lot of variability. But sometimes you're more tolerant of higher CV when your experiment is tedious, meaning you have so many different steps and transfers and all of that sorts, where a lot of errors can come in. And you would say 11% CV, well, that's good for the type of experiment. So, but for methods that you're doing in the lab, let's say fat content, protein content, really having a CV of 15% is really large. It's poor precision. Now, in what cases you for sure prefer CV? I'll give you examples. I have some numbers here that I'm going to write down. Would you rather turn on another light to see, or how do you do that? How is that? Okay. Okay, let's say we're looking at the protein content in wheat flour. So your sample, maybe I should write larger letters for those of you in the back. Wheat flour. And then another one, soy protein isolate. It's an ingredient, have high protein content. And then method, let's say here you have IR, infrared spectroscopy, Or you have a DOMAS method, which is based on nitrogen determination. It's a nitrogen combustion method, which you'll learn about when we talk about proteins. So let's say we analyzed this, and it gave me, in flour, 12% protein. We're looking at protein. 12%, and your standard deviation is 1.2, whatever is the value, it would be 1.2%. That's your standard deviation. Here, you got 92% protein, and your standard deviation is, we didn't do IR, we did DOMAS. And we got 92% plus or minus 2.76%. Which of these methods, IR or DOMAS, has better precision? Ted? DOMAS. You said II, I heard that. So, why do you think it's IR? Oh, less percent standard deviation. I didn't give you the true value. We're looking at precision only. So do you still say DOMAS? To IR? Claire?
I'd say DOMAS because the amount of plus or minus error is relatively small into the 92% IR.
Thank you, Claire. So if we do CV, CV is what? We take the standard deviation 1.2 over 12 times 100. You get 10% coefficient of variation. Here, you do standard deviation 276 over 92 times 100. You get, what do you get? 3%. So the coefficient of variation here is below 5. The coefficient of variation is 10. What happened here is the CV corrected for the size or the measurement size of your sample. So looking at the standard deviation where you're comparing two methods and two different products, you cannot really just look at standard deviation because it's not apples to apples. If you're doing, let's say, IR and DOMAS for wheat flour, and you got here, let's say, 11.59 plus or minus 0.67, then DOMAS has a better precision. You don't have to calculate coefficient of variation. It's obvious. You have very similar averages. It's the same sample. You're comparing apples to apples, not apples to oranges. Then you can just look at standard deviation. This is a very common question you would see in a quiz or exam.
So would you always factor in coefficient of variation
Sorry? Would I always?
factor that in?
The coefficient of variation?
Yeah.
No, you can, but what I was saying here, if you are just comparing the same sample, two different methods, you don't have to do CV. You do not have to calculate because you have it's the same average, basically, similar average, same sample. You will just look at standard deviation. So you really don't have to do the CV. But you could. If everything else you're measuring CV for, it would be good so that you'll have the same measure to determine precision. In the lab, I would always ask you to do CV, just to avoid the issue of, are we comparing apples to apples or apples to oranges? Okay? Now, confidence limit. Are you familiar with this? I hope I updated the page. You might, in your handouts, the page might be off. I updated, I think, based on,
It's the same.
It's the same? No, then I did not update it. confidence interval would be on page 49 in your new edition. But anyway, um, have you heard of this term, or do you know what that means when you determine the confidence interval? What does it mean when you have a, yeah, right.
You can say with a certain percentage of confidence that the true value lies within.
Perfect, yes. So usually you go with 95% confidence. Sometimes you can reduce that to 90% confidence. And you can say, as Riley said, that your true mean lies within this range. You're 95% confident that your true mean lies within this range. How do you calculate that? So it's your average plus or minus a t-value or a z-value. So depending on the number of samples. So if you have replications greater than 25, which is not really the case here unless it is a sensory evaluation, for example. You have multiple replication, multiple panelists. For example, that's when you could use a z-value. But in our case, mostly your replication does not exceed 6. So next week, you're going to do up to 6 replications. And in future labs, it will be 2, 3, or 4 replications. So you're always going to be looking at t-values. So the t-values will be on page 49 in your chapter 4, and how you would read that table. I'm sure you've seen this in a statistics course or in the sensory course if you've done that already. But you would search for the degrees of freedom. The degrees of freedom is n minus 1, or number of replication minus 1. Let's say you have 6 replications, so your n will be 5, or your alpha, sorry, will be 5, which alpha is the degrees of freedom. And then you look at what level of certainty you want, 95, 99, or 99.9, and then you get the t-value from that table. Okay? And then you multiply the t-value by the standard error. The standard error is standard deviation over the square root of your replication. Then you will get the average plus or minus a certain value. That means you will get that range from the lowest value to the highest value. Okay? Let's do this. And okay, so the t, do you want t value or z value in this case? T value. So let's say we want 95% confidence. So your t value would be, so you have how many reps? What's alpha? Alpha is? No, n minus 1 is alpha. So you have 3 reps. So alpha is 2. So in the table, I look for the alpha 2 and 95% confidence. Your t value is 4.3. You're done? Oh, it's fast. We'll wait a couple of minutes, or 1 minute. Okay. So who would like to give the numbers? Go ahead, Nan. Okay. Okay. Yeah. So the confidence interval, you can either write it in this format, plus or minus this value, or you can actually calculate this number minus this value, so you will get the lower limit, and then you can get the upper limit. So you can report it as lower limit, upper limit, or the average plus or minus that number. Okay. So sources of errors. There are plenty, and I would say infinite number of sources of errors. That could be very creative. Every year we find a very creative source of error that you guys come up with, which is very entertaining. And we have a list of sources of errors in the lab folder and in your lab packet if you have it, to give you an idea what kind of errors you might happen to have. But they are clustered into 3 categories. Systematic error, that means you're always getting the same error. Let's say the pipette that you're pipetting, it's always, instead of giving you 1 ml, it's always giving you 0.95 ml. What does that mean? When you're always getting the same error each time. Well, it's right there. Pipette is incorrectly calibrated. So I have the answer up here. So we need to check the calibration of the pipette at that time. So it could be a balance that needs calibration. It's always giving you the wrong weight of a sample. It could be a pipette that needs calibration, or there are a bunch of other like systematic errors that we might run into. That is always related to an instrument usually when it's systematic, more than a human error. Huh?
Will we be using the plus or minus standard deviation calculation with the true mean? Like if it is 1 mil, you're trying to pipette the calculation for that, would you use 1 mil plus or minus?
To determine the systematic error?
Yeah, or just to do all of that.
So you would usually determine that when you get the same percent relative error all the time. You're always having the same difference between your whatever you're getting value and the true mean. That would be an accuracy problem. Yeah, not necessarily precision. Precision is more of a variable error, is what you would get with precision, and that lies into the random error. So it could be, the random error could be something like Ryan, for example, is doing the assay and Monique is doing the assay, and they both have different values, slightly different value. This is random depending on the person that's running the assay. Another one is, let's say you are measuring a sample to determine fat percent on a balance, and then you came the following day after your pan is dried or whatever, and then you used a different balance to measure. So the different balances have different variability and different accuracy. So you will end up with a different incorrect number. Random errors could also be how you read the meniscus. You might read the meniscus in a pipette different than your partner in the lab. So there will be so many different errors that you will judge whether they are random errors or systematic errors. We'll talk more about that in the lab. Blunders, it's like, okay, it happened quite a bit, or it happens quite a bit. For example, you are titrating a sample and the color never changes. You're expecting to have goes from colorless to pink or pink to colorless, and nothing happens. You are titrating and titrating and nothing happens, and you find out that you picked the wrong reagent. Instead of titrating with NaOH, you're titrating with HCl. Or in one of the labs, we make it even harder, where we're titrating with a reagent that is 0.1 normal, and we have another reagents that 0.01 normal for another assay, and instead of picking the 0.1, you pick the 0.01, and you're titrating and titrating, and you have to fill the burette 5 times, and you still don't get a change in color. So yeah, these are blunders. Okay. Which of the following is correct for sensitivity? Nobody's going to courageously answer this question. Lauren?
C, for sure.
Lauren says C. Ryan? B and C? Katie? Yeah, we have a variety of answers here, but one is correct. B is actually a detection limit. So sensitivity is C alone. So detection of one constituent is specificity. This is B is detection limit, C is sensitivity. Sensitivity in a sense that when how low of a value you can detect, or a difference you can detect between different samples. You can detect a 0.01 molar difference, or you can detect a 0.1 molar difference. So the lower the value or the difference you can detect, the more sensitive is your method. Detection of only one constituent is specificity. So I gave that example last time. I believe if you're measuring total carbohydrate, it's not specific for glucose. For glucose, you need to do an enzyme assay to just determine glucose, for example. You're going to be fitting standard curves quite a bit this semester. And it starts with the caffeine lab. And we will walk you through how to fit the standard curve at the beginning of that lab. But why do we need standard curves? Simply. It might be in your... Why do we construct standard curves? Katie. More easy to look at the data, partially correct, Billy? Not use as a reference, use to calculate unknowns, basically. Yeah. So that's it. Use to determine unknown concentration. So you will have, I'll explain that in a minute, but you would determine the concentration of a substrate only when you have a proportional correlation. When you do have a correlation, and often, not often, most of the time in food analysis, you work with linear regression. That means you have a linear relationship between the amount and the absorbance, for example, if you're measuring absorbance. So the linear regression, you always have your independent variable. To construct the standard curve, you would prepare standards, and you would prepare them at known concentrations. So these are your independent variable, the known concentrations of your standards. And then the dependent variable changes when the concentration of your standard changes. So it's dependable on your independent variable. So y-axis we always have the y-axis as dependent variable. Of course, you can switch them, but let's keep x-axis independent and y-axis dependent. And then you get the coefficient of correlation, which is how well your data fits a straight line. And then the R squared, which is the coefficient of determination, how much the measurement is explained by the regression equation. So you will always get a regression equation that we'll use to calculate the concentration of the unknown. So the R squared closer to 1, you would have more accurate results, more closer to the true value. So here's an example of a standard curve. example of standard curves you will be preparing, but you won't be doing a BSA, bovine serum albumin standard, or would they? For the Bradford assay? But won't they use bovine serum albumin as a standard? Yeah, so you'll do that then in one of the labs. So what happens here, you prepare bovine serum albumin standards at different concentrations, multiple ones. We always want to have at least 4 or 5. The more you have, the better your chance of getting really high R squared. And then the more you have, you can eliminate odd data. Then you would say, well, this is really odd. Let me eliminate this. Your R squared will become better. So your prediction is better. And then on the y-axis is an absorbance, because this is a spectrophotometric method. So you will combine the BSA with a Bradford reagent. You will get a certain color that you would measure at a particular wavelength, and then you'll get an absorbance. You plot absorbance of the different concentrations, and then you will get scatter plot. And then with that, you get equation of the line. That's your regression equation. And your R squared to tell you how good is that, the prediction of that equation. And then, so after you have your standard curve, then you run your sample, which is unknown. You don't know how much, in this case, you're measuring protein. You don't know how much there is in your sample. So you know the absorbance of that unknown sample. You plot, you put the absorbance here, and then you solve for X. Significant figures. We all love significant figures. Okay, let me give you a few examples. I will make them simple, but we will run into non-simple examples in the lab. And as Cindy says, use your common sense at that point. Okay, so simple. I do have a bunch of numbers here. Okay, going back to your middle school math or freshman math. Okay, 64.72. How many sig figures do we have? 4, yay. How many significant figures do we have? What did you say? Well, it is 3. All zeros after the decimal point. If you place zeros, then you are stating that these are significant and you're confident that this and this is 0. What about yes, anything to the left is non-significant. All right, what about 1? Anything to the right? But let me put 4. Last one. Yeah, okay. So now we know our significant figures. Now how do we determine how many significant figures? When we have a mathematical equation. So let's say you're adding and trying to get an average number. So you're adding 2 values. How many significant figures should your answer be? 2 decimal points. Is in this case, when you're adding or subtracting, you need to have 2 decimal points. So it is 6.18. So you actually have 4 significant figures. Okay. If you're multiplying or if you are dividing. So let's do a multiplication. You'll be doing a bunch of multiplications and division for calculations in the lab. So in this case, how many significant figures should your answer have? So the answer to this is 9566. This is the actual example answer. So how many significant figures should your final answer be? 2, Mallory, yes. Because you go in multiplication or division, you go with the least significant figures. It's not with the decimal points in this case. So in this case, you round up to 2 significant figures. Okay, I'm going to give you another example. That you will be converting, you will be diluting samples, and then you're going to have a factor, dilution factor, to calculate back the original concentration. So we'll do an example of that. Okay, so let's say you are calculating caffeine, and you ended up with a concentration of 43.5 micrograms per milliliter in your sample. But this sample, before you were able to get the caffeine content, you had to dilute 50 times. You took a 1 milliliter of your original coffee, let's say, and you made it up. You used a volumetric flask. You took 1 ml of your sample, and this is a 50 milliliter volumetric flask. And then you added your sample 1 ml, and then you made up the volume with water. So you dilute it 50 times. So in order to get the concentration of your original sample, you need to multiply by 50. So if you do that, you'll get 2175. How many significant figures should this have? 1. So you end up getting this value. But there's a problem with this value. You actually reduce the sensitivity of your method because you took away these numbers, so now you cannot detect that small of a difference between your samples. So one thing we missed, it's a volumetric flask. So the confidence of this in terms of the actual volume, you are confident up to here, first decimal point. So it's not really 50 ml, it's 50.0. We're confident here, up to here, with a volumetric pipette, volumetric flask. So then this changes things. So now you have 3 significant figures. Then you can say 2180 is the concentration of your caffeine in your sample. Yeah, because, yes. So the 1 ml, that's a good question. So the 1 ml that you add, you would normally use a mechanical pipette, and on it you would see to which confidence it is, 0.01. So 2 decimals after. It would tell you, right, Cindy? It would say on the mechanical pipette.
It says on the pipette, but it says on the booklets.
It's somewhere. So you would know what it is for the mechanical pipette. But it's often, at least you are confident to the first decimal, depending if it's a volumetric pipette, burette, or volumetric flask, or mechanical pipette. Each will have a confidence in terms of where you can be confident and call this a significant figure. So now this is straightforward. We won't get always straightforward. And we will talk about that more in the lab, when you would really want to use your common sense, when the Excel is going to give you 5 decimals point, where do you draw the line, what's the equation, and all of that. We'll talk about this more when we have examples. Okay, so rejecting data. You will probably need to do that a few times during the lab. So example, you will be running HPLC, caffeine, but as a group, you will be producing 2 replicates. Another group will be producing 2 replicates of the same sample. So you'll end up having 4 replicates. So you have multiple people. So there is prone to have one sample that is odd. Sometimes 2 samples are odd, but then we are in trouble. Let's say you have collected 4 replications and one of them was really off, either way higher or way lower. So there is a way to determine if you want to reject that data point and not include it in your average so that you don't skew your precision or accuracy. So what you would do a Q test, and that's basically you take the value that is very off and you get the difference of that between this value and the closest value to it. Okay? So you get the difference of that, and then you divide it by the range of your data, the minimum value and the highest value, and then you would use a Q test table, a Q value table, and that is on page 65, I believe. No, I did not update that either. So on one of the pages of your books, that would be 57. I thought I updated. I must not be dreaming. Anyway, so there is a Q table, Q values table. So you would need the number of observations if you have 3 reps, 4 reps, or whatever, and then associated with that would be a Q number. If your Q value is greater than the tabulated value, then you reject your data point. If it's lower, then you would keep it. So oftentimes you need to do this test and present it in your lab report to validate why you took out a replication. And sometimes you do the Q test and say, well, I can't take that replication out because tabulated is, because calculated is not higher than tabulated. Okay, we have 3 minutes left. So I'm not going to start a new chapter, but let's do recap questions. What is? The recap questions? Not on the thing that you want to submit, no. If you want to keep it for your own knowledge, you can write it down. But basically, we covered all this. This is what I would like you to remember out of this lecture and some other details. But difference between accuracy and precision, we said that at the beginning of the lecture. We talked about difference between threshold and sensitivity, right? So threshold is the lowest, or is the limit, detection limit. You can take a picture of that too, yeah, that's fine. And sensitivity is the lowest difference you can detect between samples. In what case CV is better than SD, and we gave examples about that. So when you have different means, different size, measurement size of the means, then CV would be a better. When it is the same sample and you are measuring the same component using 2 different methods, then you don't really need CV. What's the difference between systematic error and random error? Oftentimes, systematic error is tied to an instrument or tool you're using in the lab. Random error could be anything. Give an example of blunder type. You will have lots of blunders during this semester. Things we've had before, things we've never had before. So you'll come up with your own list. And then knowing how to report significant figures, and this is annoying, but hopefully we'll get through it somehow. And then know your Q test, because you will be using it. Any questions? We're good? Yes, those that you have used to calculate the papers, bring them up here. This is for +2 extra credit. Make sure you have your name on it.